Continuing our work with statistics, today's lesson is on variability, and our objective is to find the variance and the standard deviation of a set of data and to convert to standard values. So as far as statistics goes, which is a number that describes some characteristic of a set of data, we've talked about measures of center being mean, median, and mode. Those are all considered averages and so on. As far as measures of spread, how far spread out the numbers are, how variable they are, how they vary. Measures of spread are range, which is the maximum minus the minimum. Interquartile range, which is your third quartile minus your first quartile. And then the two we're going to talk about in more detail, which is the variance and the standard deviation. Now the variance is the mean of the squares of the deviations from the mean. Okay, so that is a very loaded definition. But what that means, if we're talking about a set of data that has, let's say, a mean, which is symbolized by x with a bar over it. Let's say the mean is 5. And one of my numbers in my data set is 7. Okay, so 7 deviates, which means how far from the mean it is. It deviates from 5 by 2. And then we would square that and get 4. And so the variance would be the mean, the average of all of these squared deviations. And this will become more clear once we talk about the 3-column method. Then standard deviation is the positive, standard deviation is always a positive number, the positive square root of the variance. So just a quick meaning of this. If two classes took a test and they both had an average or a mean score of 85, but one had a standard deviation of 1, while the other had a standard deviation of 5. What this would mean is this class that has a standard deviation of 1 doesn't have much variability. A lot of them would have scored very, very close to the mean of 85. If the standard deviation is higher, that means the scores are more variable, more spread out. There would be a very low score, maybe very high scores in the data set. Same as we're talking about two basketball teams having an average height of 74 inches. But if one team has a standard deviation of 0, if your standard deviation is 0, that means there's no variability whatsoever. That would mean every player on the team had a height of 74 inches. If the other has a standard deviation of 4, that would mean that there's some variability there, and there might be a very tall person and a very short person on this team. So calculating variance and standard deviation using the 3-column method. The first step is always to find the mean, which is symbolized by x bar, the mean. So I'm going to add up these numbers, and I'm going to divide by the total number, which is 6. So I have a sum of 54 divided by 6, so I find my mean to be 9. Okay, so then I'm going to use the 3-column method. So I'm going to list the numbers, put them in a vertical column. And my second column is going to be my deviations, how far from the mean they are. So 4 is 5 below it, 6 is 3 less than 9. 9 is, there's no deviation there. 10 would have a deviation of 1, 10 would have a deviation of 1, and 15 would have a deviation of 6. Then my third column is going to be my deviation squared. So I'm going to square that second column. And then as you remember our definition, the variance is the mean of these squared deviations. So I will add this column up. So 25 and 9 is 34, and 1 is 35 and 66, another 36. 72 is the total of that column. And I would divide that by 6 because there are 6 numbers. So that number is 12, which is the variance. Then your standard deviation would be the square root of 12. Which is about 3.5, rounded to the nearest tenth. So another example here, we've got the numbers 5, 5. I'm going to write these vertically. And I'm going to find my mean, so I'm going to add these up. They add up to 49. 49 divided by 7, 7. So my mean is going to be 7. Okay, so my second column is my deviations. -2, -2, -1. 7 is the mean. And then 5. I'm going to square that column. And I'm going to add this column up, which gives me 34. I'm going to divide that by, there's 7 numbers. Divide that by 7. And my variance in this case would be 4.86. Standard deviation is then in the square root of 4.86, which would be about 2.2. So this was less than the previous one we did, because if you look at the numbers, they are very close together, except for the 12, which could potentially be considered an outlier in this set. Using technology to find the standard deviation variance, the 3-column method is a very quick and easy method of finding this if there's only a few numbers, all of them being whole numbers, and of which the mean is a whole number. If you have a long list of numbers where some of the numbers in the mean are not whole numbers, the 3-column method can be very time-consuming. Using a graphing calculator to do this, you would follow these methods. And you might want to just practice this with, let me give you these numbers. Let's do it with the numbers 3, 6, 10, and 14. So what you would do is go to Stat on your calculator, and then you're going to go to Edit. Once you go to Edit, you would create a list of numbers. I'm going to do this under L1. So I would just type in those numbers, 3, 6, 10, and 14. And then I'm going to go back to Stat and go to Calculate. I'm going to calculate one variable stats, which is number 1. So I hit enter on that, hit enter again, and it gives me a list there. It gives me X bar, which is the mean of these. That's 8.25. It gives me sigma X, which is 33. That's the sum of those 4 numbers if you add them up. It gives you sigma x squared, which is the sum of all the squares. That would be adding 9, 36, 100, and 196. That's 341. Then it gives you Sx. In this case, it gives you to be 4.78. This is a sample standard deviation. It also then gives you theta x, which is 4.14. This is the population standard deviation, and this is the one that we've been finding. The only difference is the sample standard deviation, like instead of dividing it by 4 in this case, they would divide by 3. But we're gonna use this type of standard deviation consistently.